In this video, I want to take a look at the symmetric equations for a line. So the simplest way to describe a line in 3D is to give a point that it goes through and a direction that the line is parallel to. And we've seen in a previous video that the parametric equations then would be this. X equals the x0, the point you want it to go through, plus at, where a is the x component of the direction vector. Likewise, y equals the y component that you want to go through plus b times t, where b is the y component of the direction vector. And likewise for z, z is z0 plus ct, where z0 is the z component of the point you want to go through, and c is the z component of the direction vector. Okay, so this is parametric equations. Now, one thing about parametric equations, the way it works, is you pick a value of t, you plug it into all three equations, the same value, and that gives you coordinates x, y, and z. You make those three coordinates into a single point, and you plot that point. Then you pick a new value of t, you plug it in to get x, y, and z again, and you plot a second point. So that at each point on the curve, in this case it's a straight curve or a line, it's the same t value giving you the x, y, and z coordinates. So what we're going to do is we're going to solve for t. We're going to essentially try to eliminate the parameter. If you think about in 2D, we had a couple different ways of doing curves. You had equations that had just x's and y's, and then you had parametric equations. And when you first learned about parametric equations, you learned somewhat about converting back and forth and going from parametric to just an xy equation. That was called eliminating the parameter. And that's essentially what I want to do here. So I'm going to solve each of these equations for t. So the x1, I solve for t by subtracting the x0 and then dividing both sides by a. Likewise for this one, subtract the y0, divide by b, and subtract the z0 and divide by c on this last one. So I have that t is this, or that, or this. And since it's the same t, they're all equal to each other. Right? If you've got a point x, y, z on the line, it was the same t that got the x coordinate, the y coordinate, and the z coordinate. So those are all equal to each other. So we set them all equal to each other. And now I have, well, I almost said I have an equation without the t in it, but I don't. I have actually three equations. And it might look like two equations because there's two equal signs there, that the first one is equal to the second and the second is equal to the third, but it's also true that the first is equal to the third, right? That there's three equalities there. So this is not just a single equation describing the line. This is two or three equations, however you want to think about it. And really what it is intersections of planes. If I were to ignore the last part here, the z minus z0 over c, and just say x minus x0 over a equals y minus y0 over b, if I was in the plane, then that would just be a line through the point x0, y0 parallel to the vector AB. Okay? But I'm not in the plane, I'm in space. So what you do is you take that line in the plane and extrude it in the z direction. Right? So these first two, just that single equation there, is describing a plane in space. Likewise, if I just took the last two, ignoring the x's here, I would have what looks like an equation with just y and z in it. So you might think of that as a line. It's a linear equation with y and z, so you might think of that a line in the yz plane. But because we're in space and there's no x's in that equation, then you can just extrude in the x direction and you'd have a plane. So this equation described a plane and this equation described a plane. If you think about what happens, where do two planes intersect? Two planes intersect in a line, right? That line, let's see if I can do this. Two planes intersect in a, forget it. Two planes intersect in a line. You can see I'm looking right down the line of where my fingers are crossing there, right? That I'm not describing the line with a single linear equation. I'm describing the line with two linear equations. Each equation is describing a plane. Those planes intersect, and that is where the line is. In some ways, it's three equations, again, because you'd have this. So here's a quick example here. If I want the line through the point 1, 2, 4 in the direction of minus 1, 2, 1, then these would be the parametric equations, right? The 1, 2, 4 is the x0, y0, z0. The direction vector, minus 1, 2, 1, you can see it here, minus 1, 2, 1. And the symmetric equations look like this. Now I want to take a look at the picture of this example here. Let's pull this up. So what I have here is, how do I want to orient this? So I'm going to put this with the positive x coordinate running this way, the positive y coordinate running out there, the positive z coordinate going up like this. This is the point 1, 2, 4, and the direction vector, although it's not drawn in there, is minus 1, 2, 1, as the example has. Now I can see that, for instance, if I were to look right down the, this is looking straight down the x-axis, and so I can see in the YZ plane, this looks like for every 2 that I go over, it goes up 1. So that's the 2 of the direction vector and the 1 in the Z direction, right? 2 in the Y, 1 in the Z. Likewise, if I look straight down the Z axis, I can see the relationship between X and Y. So I'm going to look straight down the Z axis here, if I can get it the way I want it. Yeah, so I got the X axis running that way and the Y axis going up like that. You can see from this point, if I go backwards 1 in the x direction, and I go up 2 in the y direction, so that's the negative 1, 2 for the vector parallel in that direction. So this is the line that I want. Now, think about that equation right here, with, forget about the z's, just look at this equation, right? In the xy plane, this is the equation of a line. In fact, I think I'm looking at that line right now. This is, if you just project this line straight down onto the xy plane, this is what it looks like, and that's its equation. But then if you think of this as the equation of a plane in space, right, there's no z in this equation, so I'm ignoring that part. So this would then just be extruded parallel to the z-axis like this. Let me see if I can look at it. Oh, there we go. Okay. So this green plane is the plane determined by this first equation here. X minus 1 divided by minus 1 is equal to y minus 2 divided by 2. Right. Z is not specified in that equation, so this plane is parallel to the z-axis. Right? What just happened? Right. It's parallel to the z-axis, and the line that I'm interested in is completely contained on that plane. Likewise, I could look at forget the x's and look at this equation here with just y and z. That would be, if I look straight down the x-axis, let's see here, if I look straight down the x-axis. Now, of course, this green thing is in the way, but you would have the line in the yz plane, which we already did. But we can now turn that into a plane by letting x be anything it wants, and what we have here, oops, there we go, we have another plane that is now parallel to the x-axis. And notice that that plane is parallel to the x-axis. Can I see that maybe right here? Stop. Right, this plane is parallel to the x-axis. It also contains the line that we're interested in. So the green plane, which is this first equation, and the blue plane, which is this second equation, intersect in the line that we want. Now, just for completion here, let's put that last equation in. That is x minus 1 over minus 1 equals z minus 4 over 1. So let's put that in. And there is the red one. This red one now is supposed to be parallel to the y-axis. So, yeah, there's the y-axis, and there's that red plane. Notice I happen to be right at the spot where I'm looking straight down the intersection of all 3 planes. All 3 planes contain the line that I'm interested in. Take any pair of these, the y and the z, or the x and the z, or the x and the y, you're describing a plane. Take 2 of those pairs, and you're describing the line of interest. These are called the symmetric equations for a line. Now, I will admit to you that pretty much every Calc 3 book that I've ever learned from or taught from goes through symmetric equations of a line. I have never seen them anywhere else. I've never used them at all in everything that I do. I'm not really sure why it's always in the free books, but there it is. You're talking about a line by giving a couple of equations of planes, and the line you're interested in is the intersection.